Okay, thanks for Ryan's very kind introduction, and it is so I'm very glad to get invited by IPAM, and thanks for the organizers to give me an opportunity to present our work here. Okay, so this is based on joint work with Jianfeng Zhang from USC. Okay, and I will somehow divide into three parts to talk about the result. So first, I would like to talk about some background. Okay, and then I would like to talk about our wellposedness results. And hopefully at the end, I have time to talk about some of the convergence results, okay, by applying our wellposedness results. Okay, so let us start from the background, okay. So this is the mass equation we consider, okay, and this is with the individual noise and the common noise. And so I want to say that it is non-degenerate, okay. What I mean non-degenerate is the coefficient in front of the individual Brownian motion is strictly positive. So without loss of generality, we assume here is 1, okay? And then for the common noise, the coefficient is beta, and which is not need to be positive. It could be 0, okay, but non-negative. Okay, so and then so now let me briefly talk about what is this mass equation, okay? So this is satisfy this terminal condition first, and then we consider on the domain, which is RD, which is non-compact. It's not compact. Is RD and for arbitrary dimension. And then we consider so P2 means the second, so this is the set of probability measures with the finite second moment, okay, and maps to R. For I would call F and G later just coefficients correspond to this mass equation. And so we consider general Hamiltonian here. Okay, and then we have a lot of non-local terms due to the presence of the individual noise and the common noise, and also the drift. Okay, so because it involves the common noise, so we have this second order term with respect to mu. Okay, so we have this second order term, and so not hard to see that if beta is equal to 0, so that means there's no common noise, then you do not have this second order term. Okay, and also I forget to talk about what is this partial mu here. So partial mu here is the Wasserstein derivative. Okay. And whenever we take this Wasserstein derivative, actually we have, so originally V has a 3 variable. And if we take this Wasserstein derivative, we have one more variable coming out. And this is, I would call it x tilde. So here I have a partial x tilde, partial mu. So that means I take a further derivative for this x tilde. Okay, and then also I have a partial x or partial mu. So this is again coming from the common noise. So if there's no common noise, you do not have this term. Okay, and again, if you do not have a common noise, you do not have this beta squared. Okay, and then if you also remove the individual noise, then you do not have this Laplacian. Okay, and then you also do not have this term, but you still have this non-local term here. Okay, and this is the non-local term for the gradient. Okay, and this non-local term here is actually somehow bad in the sense that we cannot start with viscous solutions. Well, this is non-local terms for the gradient. Okay, and then you know that by the definition of a viscous solution, it touches from above or below locally, but here is globally in partial x. So there's no way you can use viscous solution here. And then again, because the Wasserstein derivative here is an infinite dimensional derivative. So I think there's no way you can use integration by parts formula here. Okay, and then so it actually makes the weak solution infeasible. Okay, and that's why it's hard to find weak notion of weak solutions here. Okay. Okay, so and then so now I want to somehow talk about how to derive. Oh, so sorry. I also want to somehow explain what is the purpose why people started this mass equation. So actually, there are two purposes. So one, so you have somehow opposite directions. One is so if you start this mass equation, it can help you somehow to use this mass equation to use this mean field games to approximate n player games when n is sufficiently large. So actually, this is sufficient if you only study the mean field gain system. But if you study mass equation, it have extra information because you know how does the Nash equilibrium depends on the population or the distribution of all the others players. And then another way is whenever you study this mass equation, it can help you to find somehow to study the convergence from n-player games to the mean field games. Okay, so this is the other directions. So this mass equations help you to somehow to study the both direction. Okay. Okay, so now I would like to somehow briefly talk about how to derive this mass equation. Okay, well, this could be has better understanding of what is that. Okay, so actually this is coming from the Nash equilibrium of the mean field games. So Kasai here is actually the initial data for the individual player. And the law of Kasai is mu, and also the mu is the initial distribution also for the population, okay? And then this x Kasai alpha, alpha is the control, okay? It satisfies this equation, okay? And the BT here is the individual Brownian motion or individual noise. And then BT0 here is the common noise or the common Brownian motion. And then, so this is somehow you can view this as a Fokker-Plana equation, okay? And you can view the following thing. This is actually a BSD, backward stochastic differential equation. And you can somehow view this as a Hamilton-Jacobi equation because you can think about this y is the value function, okay? But by given the control, okay, by given the control. And here is, I want to say that we have two controls here. One is this alpha here is actually the control for the population. And this alpha prime is the control for the individual player. So at the beginning, we fix the control for the population. Okay, so we fix the control for the population. So you see here is alpha, and here is conditional on the common noise. Okay, conditional on common noise. So I want to say that this is a random error. This is variable with respect to the filtration generated by the common noise. Okay, and also here is the individual control. Okay, so first you fix the control for the population, and then you somehow want to maximize over all the alpha prime. Okay, and then so first I define my cost function. So this is my cost function. Okay, so whenever you take expectations, then you go back to here. You do not have these two terms. Okay. And this is the the value function or the representation formulas for the solution of the Hamilton-Jacobi equations. Okay, so here again it depends on alpha and alpha prime, and then I said I want to fix alpha and then maximize over alpha prime. Okay, so this is my maximization problem I want to study. Okay, and then later I want to study what is the Nash equilibrium here. So what is the Nash equilibrium for the mean field gain? Is we say that alpha star mu star is a Nash equilibrium for the above mean field gain problem. If we first let's say the population now is choosing the Nash equilibrium alpha star. Sorry, alpha star, and then the optimal strategy for the individual player is again the same thing, which is alpha star. Okay, then we call this somehow this alpha star is the Nash equilibrium. Okay, and then the optimal somehow this is the path or the trajectories for the population when everybody is choosing the Nash equilibrium. Okay, and then again this is a random error. Okay, so now I would like to derive the mass equation. Okay, so by comparison principle for the BSDs, or if you are not familiar with BSD, I want to say that this is somehow equivalent to the Hamilton-Jacobi equations. So I mean the comparison principle for the Hamilton-Jacobi equations here. Okay, and the definition of a Nash equilibrium. Okay, and then you will find that actually the Nash equilibrium solve or the trajectory is satisfied by the Nash. You choosing the Nash equilibrium satisfy the following dynamics. Okay, and then so the optimal strategy for the not only so this is the Nash equilibrium is given by this partial pH xt alpha star and the zt alpha star, and here we have a bt alpha star. This is given by this formula. Okay, and the alpha star is coming from here. Okay, so somehow you add a drift to the original Brownian motion. Okay, So I do not want to talk about details about how we derive this FBSD system, but I want to say that it's coming from the concurrence principle and of the BSDs and also the definitions of a natural equilibrium. Okay. Okay, so then I somehow translate the original FBSD to another FBSD. They are equivalent. Okay, in the sense that the mass equation behind this FBSD, they are the same equation, the same mass equation. So this is why I call it they are equivalent. Or you can get it from the Gasanov theorem. Okay. So instead of studying this one, we study an equivalent FBSD. Okay. Again, here mu t here is a random error. Okay, if there's no common noise, then this is determinist. Okay. And then we define somehow this value function Vt cosine is by this Vt xt cosine and mu t. And you might wonder that why this is well defined. Okay. This is coming from the uniqueness of this, at least locally, uniqueness of this FBSD system. Okay, and then instead, like ODE, if you have this uniqueness, then you can define flow, and right, it satisfies the flow property. So that's why actually this FBSD somehow depends on the initial data. Okay, and then that's why this YT cosine at time t, it depends on only somehow the XT cosine and the mu t. So this is somehow the flow property. And that's why this is well defined. It's coming from the uniqueness. Okay, and then it can be shown that this V satisfies the mass equation. Okay, and then with the terminal condition. Okay, so it's not hard to see that it satisfies the terminal condition because of this. YT cosine is a G of XT cosine and mu t, right? Because if you take t, then you do not have these two terms. Okay, and how to derive the mass equation? So it is also not hard. So from this FBS, from this BSD, you know what is a dyt cosine. Okay, and then you also can do the Ito formula for this VT because they are the same thing. Okay, so VT xt cosine and mu t. Okay, again this is random error. Okay, so first you need to use the Ito formula for this one, and then obtain that. I don't want to write down what are they. They are quite complicated. So here you have three terms. So dt term, dbt term, and then plus and plus dbt0 term. Okay, the common ones. And and then compare the coefficients, right? So you can compare the coefficients. I don't want to write it down. You compare the coefficients for these two terms. So you first compare the coefficient in front of dbt, so the individual noise. Then you get the zt cosine is equal to partial x v t xt cosine and then mu t. Okay, and then you apply this, and then by comparing the coefficient in front of dt term, and then apply this one, you will get the mass equation. Okay, I will skip the step. But this is basically the idea how to get this mass equation. And I also want to mention that you see here is ZT of a star. So if you plug this in, so you see the optimum control is the same as somehow you derive from the PDEs. Okay. So this is how we derive the mass equation. Okay, and so you know that from this somehow this famous book or this long paper by these four authors, Cadaraguet, Dallery, Lassuy-Lyons, they use a mean field game system to study the mass equation. And the crucial estimate there is the global Lipschitz estimates for the solution of the mass equation with respect to the mu variable. What I mean is for the probability variable. Okay, that is the crucial thing. And now I would like to derive the mean field game the mean field game system here. Okay. So the mean field game system here is SPD system, so stochastic partial differential equation system. Okay, so how to derive that? For the Fokker-Planck is just follows by the classical somehow the derivation of the classical Fokker-Planck equations. But the only thing different here is we condition on B naught, right? So the classical one to derive is you take expectations of a phi of xt psi here, okay, and then do Ito formula, you will get the Fokker-Planck equation. But here, the only thing you need to change is you add this conditional, and then do the Ito formula. You will obtain this stochastic Fokker-Planck equation. Okay, you get this stochastic Fokker-Planck equation. And then to derive the stochastic Hamilton-Jacobi equations, so this is the stochastic of Hamilton-Jacobi equations, you need to somehow do like the individual noise case, or the degenerate case is you define UTX here is equal to V of TX mu T. You plug in somehow the optimal trajectory for the population, or the governed by the Nash equilibrium. You plug it in, and then you take the derivatives with respect to T. And so basically, the idea is similar to the derivation of the mass equation. So I will just very quick to talk about this. So you know that Txt psi is equal to dy what? Sorry, I don't know how to. Let me start one more time. Okay, perfect. Du txt psi is equal to V txt psi and mu t, am I right? And then it's equal to dyt psi. Again, you compare the coefficient on both sides, and then you apply the mass equation because you already know the mass equation now. Okay, you apply the mass equation, compare the coefficients, you get this du, the stochastic Hamilton-Jacobi equations. So here, because u is so I forget to say that u actually here is a stochastic function. Again, is different is a variable with respect to the filtration generated by the common noise. Okay, because mu t here is random. Okay, so u here is a stochastic function. And then again, like just compare the coefficient, you will get this stochastic Hamilton-Jacobi equations. And I want to say that this is a backward stochastic Hamilton-Jacobi equations. Okay, and then I just want to make some remark here is the vector field. So you see here we involve some gamma here, which is unknown function. Okay, and I want to say that this unknown function, the vector function gamma, so this is a vector function, is part of the solution of this stochastic Hamilton-Jacobi equations. So what I mean part of is this is uniquely determined by the stochastic Hamilton-Jacobi equations. Okay, and then I want to say that if the decoupling field V is smooth, so let's say this decoupling field is smooth. What I mean is defined by this one is smooth. Then you can show that this gamma is equal to this one. Okay, and I also want to make a notice here is you cannot use u, because here only is a function, solution is u. You cannot use u to represent this term. Okay, again, this term, you see, this is definitely a vector function, partial mu v. Okay, but if let's say v is not smooth, so then you don't know what is exact. There's no representation formula for this gamma anymore, but you know there's an unknown function satisfied this. Okay, so this is this mean field game system, and so in our paper we didn't use this mean field game system to study the mass equation, because I want to say that if you study this mean field game master equations to derive the mean field game system to derive the mass equation, you somehow have to use this derivative derived by Lassourie-Lyons. Okay, and then I want to say that this is not an intrinsic derivative for functions with respect to have a measures. Okay, this is not intrinsic derivative here. And then the most intrinsic, so the intrinsic derivative here is actually the Wasserstein derivative. And I also want to say that, actually this derivative is actually, sometimes it's very hard to calculate what is the Wasserstein derivative. And actually this derivative defined by Lassourie-Lyons is helping us to find what is the Wasserstein derivative. Okay, sometimes we have the intuition of what is the Wasserstein derivative looks like. It's really hard to directly get the Wasserstein or calculate the Wasserstein derivative. Okay. And instead, we didn't use the mean field game system. Instead, I used this FBSD system. Okay, so the first two equation I just copied from what I derived before. here. I just copied from here, okay? And why we need to study another two? The reason is following. So now you know that if we smooth, we get everything. Okay, we derive the mass equation, we get also the mean field game system. And so this is because of the following reason. So we know that yt psi is equal to t xt psi and mu t. Okay, and let t be 0. And then now it becomes to psi because it satisfies the initial data is psi. And then here it becomes to mu. Okay, mu is deterministic error, mu. So you don't need to put a conditional. Okay, so it is easy to start the differentiability with respect to mu now because you can perturb psi here. Okay, this is easy. But how to start this differentiability with respect to the x component? What I mean is the position of the individual player. So this is why we studied this too. So the idea behind is we just take the conditional on psi equals to x. Okay, and then we obtain the following two. So if you see here, if I will take the conditional on this, we will get the right hand side is psi now has to be x, right? Okay, then we can start the differentiability with respect to this x. Okay, so this is by perturb the x variable here. You can start that. Okay, then the crucial thing is first you want to start the wellposedness for this McKinley loss of SDE, FBSD. And the second thing is you want to start the differentiability with respect to this psi and also the x. Okay, if you get that, you get classical solution. But the thing is, wellposedness is not that it's easy to study, and the differentiability is also not easy to study. Okay, so our first result is the wellposedness for this FBSD. So let me review some known results for the mass equation. So there's a huge literature about mean field game system, but here let me just talk about the mass equation. Okay, so first I divide it into two directions. One is potential mean field game, or you can say this is the mean field control problem, related to mean field control problem. And for the degenerate case was started by Ben-Susan Yan and Gambo switch, and then later was followed up by the Moyagas and also the Gambo and Masaras, and APA talked about this result on Monday. Yes, and individual noise. If only involves the individual noise, it was started by Ben-Susan, Graber, Yan, Fan, Wei, Wu, Zhang. Okay, so they also started the path-dependent case. And the common noise case actually was recently started by Gambo, Moyagas, and Switch. And Andrea will talk about this result in the afternoon. Will be in the first talk. And so for the general mean field games, so you see that here our setting is for the non-degenerate case. What I mean is, again, the coefficient in front of the individual Brownian motion is bigger than 1. But I want to say our method here can be applied to the degenerate case. What I mean is I do not have a common noise. I do not have an individual noise. We can still define the somehow weak solution and start wellposedness. I will talk about the wellposedness, what I mean by weak solutions later. Okay. But I know very little reference here for the general mean field game. So if you know, let me know. Okay. And the individual noise, it was started by Transacnews, Crescent, and Dallery. Okay. And then for the common noise case was I have already mentioned this papers written by these 4 authors, Callagher, Dallery, Lasry, Lons. Or you can do this is a book. Okay. And then also this 2-volume thick books written by the Carmona and Dallery, and both involves the commonness. And here, the first one is based on the PDE method, and this one is based on the probabilistic method. Okay. Okay, so let me somehow summarize all the previous results. So I can summarize somehow in 2 directions. So one direction is we assume that FNG are smooth, sufficiently smooth. Okay, and then satisfy some convexity assumptions. Okay, so monotonicity is a kind of a convexity assumption. Also, the APAs somehow their result is displacement convexity. Okay, so Both are some convexity assumptions. So the mass equation 1 here admits a unique classical solution for arbitrary long time t. Okay? And the other one is assume f and g just smooth without monotonicity. Then what you can get is only a short time result. Okay. And so what do I mean by smooth here? So at least they have third order derivative. Derivatives in x and mu variable. Okay, not only in x but also in mu. Okay, and they need that to derive the mass equation. Classically, you have a classical solution. Okay, so actually, I want to say that the major open problem for the mass equation is the following: is can we define the notions of weak solutions to the mass equations and show its wellposedness if the above assumptions are not satisfied? Okay, so and then if you go back to this this summary, is there are somehow two kinds of so you can relax the assumption in two ways. So one way is you somehow assume f and g are less smooth, and then you do not expect you have a smooth classical solutions. This is one way. And then there is a much more difficult way, which is you do not assume monotonicity assumption, and then you still want to define some weak solutions and show the wellposedness. Okay, and then here in this paper we started the easier one, which is we assume f and g are less smooth, but still we assume monotonicity assumptions. And then we define the weak solutions and then show wellposedness. So here we define two weak solutions, and at the end, I will show that they are equivalent actually. So that means the definition of our weak solutions have some good property here. Okay. So this is the assumptions we assume throughout this talk and the paper. And then I want to say that for some theorem, we actually need to assume less, just need to assume less than that. But here for simplicity, I just assume this and then I get everything, okay? And we assume Hamiltonian here is, they are Lipschitz, okay? I mean Lipschitz locally. What I mean locally here is locally in p variable, but globally in x variable, okay? And then I also assume that this is strictly convex locally, again, locally in p, but globally in x, okay? And then this is the assumption we assume for f and g. So f and g, partial xf and partial xg are Lipschitz in x and the mu variable. For mu, we use one Wasserstein metric, okay? And here we assume f and g are monotone, okay, to get arbitrary long time result, okay? But we can remove that to study the local result, actually. Okay, we can still define weak solutions and show wellposedness. And then for that one, for the local result, we even don't need to assume this two. Okay, we just need to assume f and g are Lipschitz in x and mu variable are in now. Okay, and I want to make several remarks here is we never assume partial mu f, partial mu g exists. We never assume they exist. Okay, although here we assume Lipschitz, but you remember that mu is in infinite d. Lipschitz does not imply that you have a derivative almost everywhere like finite d. Okay, so we do not assume that. And also, if you go back to see the mass equation, we have a partial mu term, even the second order term with respect to mu. Okay, so we never assume such a thing for mu. So I want to say that we do not expect we have classical solution with these little assumptions on the coefficients, okay? And why I want to say that is in x variable, we have individual noise to improve the regularity. But for mu variable, somehow we have the common noise to improve the regularity. But the common noise only improve the regularity in finite d, okay? Only in finite d, but mu is a variable in infinite d. So I want to say intuitionally, we do not expect we have any classical solutions here, okay? And we cannot go beyond the coefficients in some sense, Okay, so that means we have to define some weak solutions. Okay, so here is the monotonicity assumptions. And I said that this is some convexity assumptions. Why? Because of we can assume that we have a calligraph F, take a derivative. So this is the Lyon's derivative. And then this calligraph F is some potential for this the F. And then if the calligraph is, so this monotonicity means for this F means that it is convex for this calligraph F in mu variable. Okay. This is what I just want to mention. And this monotonicity assumption was introduced by Lyons. Okay, so first we started the wellposedness for the FBSDs. Okay, so I said just under that assumptions, we show that the forward-backward McKinley loss of SDs is well-posed. Okay, here I want to make two remarks. So one is we assume F and G, H are smooth. So actually this case was started by this thick book written by Dallery and Carmona Dallery. And but what is new here for the smooth case? Okay, for the smooth case, what is new here is we also get representation formulas for all kinds of derivatives involves mu. Okay, so you have an explicit representation formula. And in X variable, we didn't write that in our paper because it is easy. The mu one actually is the hard one. Okay, and then it's very technical. Okay, and but I want to say that our wellposedness actually is for the assumption we assume above. Okay, and okay, and we can show that if F and G, H are smooth, we solve the mass equation classically. We can show that. But I said this part somehow was started before. Okay. And okay, so the next step, the next remark is we actually use the monotonicity here is for keeping the Lipschitz constant of V in mu. So what I mean here is somehow this also relate to the proof. Is you studied the long time result, and then it is easy somehow to first get it is not hard to first have the wellposedness for local. Okay, so what we did is here is a G here. This is the terminal condition. Okay, and then you solve the FBSD locally here, and then so here you start from here now. So this is your terminal condition. Then you use the decoupling field at the t minus delta 1, and then you start again. Okay, but I want to say that this delta 1 actually depends on the Lipschitz constant of this F and G. Okay, so for here, it depends on the X and the mu. So we need to use this monotonicity assumption to keep track of the Lipschitz constant of the mu. Okay, for X variable, we don't need to use any monotonicity assumptions. Then, because we keep track of all the Lipschitz constant, this allows us to extend to arbitrary long time. Okay. Then I would like to talk about the wellposedness for the mass equation. I said we define two kinds of weak solutions, and later we show their equivalent. So this is our first solution, which is a so-called good solution. So what I mean, good solutions here, you don't need to go through this definition because it has 4 lines or 5 lines, but I will just briefly use a picture to show you what is that. Okay. So 0 to t. And then if we say V is a solution from 0 to capital T is the following. If you have, let's say, a small interval, arbitrary small interval in between, okay? And then here you have a Vn, which is smooth in this interval. Okay, at the terminal, for this short time, Vn T naught goes to this V. And then I use this, somehow I simplified the mass equation by using this notation is alpha V is equal to 0. This is just a nonlinear operator, okay? Show up in the, let's say, the mass equations. And then if we can have these operators, Vn, so this means that Vn satisfy a perturbed mass equation. And then when n goes to positive infinity, it goes to 0. So this is in between. So this means that it satisfies a perturbation equation, and the perturbation goes to 0 as n goes to infinity. then we can show that for maybe a smaller interval, okay, we can show that Vn goes to V. Then we call this V is a good solution. Okay, and the next step is we show that the decoupling field V coming from this FBSD is the unique one, a good solution to the mass equation 1 for arbitrary long time t. Okay, under the assumption I assume above. Okay, and then also we get also the stability. Okay, and I want to make a remark here is the monotonicity assumption is only needed to construct the decoupling field. So what I mean here is this monotonicity help us to find existence, not uniqueness. So we didn't use the monotonicity to start to get a uniqueness. And you see that somehow, if you know that actually this monotonicity somehow is to guarantee that the mean field game system has a unique solution. But here for the mass equation, we don't need that. Okay. Okay, and I want to say that the crucial ingredient in our to show the wellposedness is the following: is we construct a smooth mollifiers for functions on Wasserman space. Okay, to our knowledge, this is something new. Okay, so here is let U in C0, so it's a C0 in P1 Wasserman metric, and we have a UN. So this is the constructions. I don't want to go through the constructions here. Okay, is C infinity in P2 and continuous in P1. Okay, then our construction can guarantee that we have UN goes to U in infinity sense for any compact set in P1. Okay, and then also you see that the crucial thing for us is keeping the Lipschitz constant always. Okay, so this is the result for keeping the Lipschitz constant. If U is Lipschitz with respect to W1 in L, we can show that UN is has a Lipschitz in CL, C independent of N. Okay, and here I also want to tell you the reason that why we do not use W2, because P2 is for this result is not true. We find an example. Okay, is if U, let's say, is Lipschitz with respect to W2, we find an example that the UN actually the Lipschitz constant blows up when N goes to infinity. And then for the number 3, is actually for the gradient partial mu, the convergence for the partial mu. And again, it's quite complicated. I just use a simple word to explain what is this. So basically, is we show that if U is C1, okay, U is C1 means is partial mu U mu X is continuous. So you might also ask me that only X has a sense on the support of mu. So how can you say that it is continuous? So what I mean here is it is continuous means that we can find one selection of this which is continuous, okay? Because it does not have a meaning, which is X is not in the support of mu, okay? But we just need to find one selection which is continuous, then that satisfies the C1. Okay, this is but our definition of C1 here. And then we can show that the partial mu UN here does not go to partial mu U in infinity sense. Okay, so that's why here we have an integral. We show it by example. This is not true. Oh, sorry, L infinity sense. It's not true. But we show it is true in L1 sense. Okay, which is the following thing below. Okay, and the L infinity sense also is implies it's not true if I pick a direct mass here somehow. Yes. And the one crucial remark here is our smooth mollifier does not keep the monotonicity assumption. I don't think this is the fault of our smooth mollifier, the construction of our smooth mollifier. This is mainly is really hard to keep this monotonicity assumption, because let's say for this F X mu here, if you just let us assume mu F here is monotone, And then if you only use the standard smooth modifier infinity for this x variable only, you will not keep this monotonicity assumption. Okay. So in general, it's hard to keep. Okay, and this is very bad for us because we assume the monotonicity at the beginning. If we do this as smooth modifiers, we use these smooth modifiers, we can only get a local result. Okay, we have to overcome this difficulty. So the idea behind is we solve it locally and keep track of all the Lipschitz constant, and then later extend to arbitrary long time. So and it makes the proof somehow very technical. Okay. So now I want to talk about our second notion of weak solutions. Okay, and I said at the end we show that they are equivalent.
Okay. I just want to give you a reminder, Chenchen. You got about 10 minutes.
Okay, that's good enough. Yes. Thank you for the reminder. Yes. Okay, so so here again we assume that V is not smooth in some sense, only continuous in time. C1 in X, C0 in mu, so only continuous here. Is weak solutions if, let's say, for arbitrary long time from 0 to capital T, we pick an arbitrary subinterval from this long time. Not need to be short, but it's just arbitrary. Okay, and then initially it start from mu naught at T naught. Okay, and the following SPD. So this is the somehow the stochastic Hamilton-Jacobi equation, but this is somehow of the feedback form because here is partial XV. Because this involves mu t here. Okay. So you need to somehow start it by a fixed point argument. Okay, but we assume, let's say, this one exists. Okay, we assume, let's say, this one exists. Has a weak solution. So what I mean weak solution here, because there's no mu, partial mu here. Okay, we can consider the integration by parts. Okay, I mean this weak solution is just integration by parts. Okay, so if I this stochastic partial differential equation, just define this by integration by parts. And you know that somehow I derived what is how to find the classic solution for the stochastic Hamilton-Jacobi equations is this. Okay, and then we say that if let's say V is the weak solution, if this one has a weak solution, and we plug into V here. Okay, and then U solves this stochastic Hamilton-Jacobi equations again in the weak sense. Weak sense again is integration by parts. Okay. Okay, and then this is the result for the weak solution. Okay, so we show that again under that assumption, the little regularity assumptions on F and G. We have the any function is a weak solution of the mass equation 1 if and only if it is a good solution. Okay, so this we show that they are equivalent. And that implies that the decoupling field of V of the FBSDE is also the unique weak solution of the mass equation. Okay, and the main result actually is here because this implies the second one. And you might wonder that this direction is easy. The good to weak is easy to show because you might think that this only involves, so you see our good solution only has a derivative in X. We don't have any derivative in mu. And then here, there is no derivatives in mu. You might think this is easy, but I want to say that this is not easy in the following sense. If you remember, how we derive the stochastic Hamilton-Jacobi equations is we take the derivative with respect to t for this one, and then if there's no differentiability in mu t, you cannot apply the chain rules to obtain this one. Okay, you cannot apply the chain rule to obtain this stochastic Hamilton-Jacobi equations. Okay, but you see here our good solution we don't have this differentiability with respect to mu variable. Okay, so this actually makes things hard. Okay, and how to overcome this difficulty? Again, we use smooth modifier. Okay, we have to use smooth modifier. So first we have Vn Gn, and then we get the solution Vn. Okay, and then we also get the corresponding optimal or the optimal strategy or the mu n, which is coming from the Nash equilibrium. So you have this. And I know that this one can differentiate, it is differentiable with respect to mu variable. Then we can apply the chain rule and so on. Okay, but then I want to take the limit to get this one. I need to show two convergence. One is Vn goes to V. The other one is mu n goes to mu. To show mu n goes to mu, we need partial x V n Tx mu n T, because this is the vector field. Actually, this also shows that the Nash equilibrium converges. And we are able to also show this one. Okay, then apply this, we get Bn goes to V. But again, the crucial thing is we lose the monotonicity here if we regularize this. And this is for arbitrary long time. Again, we need to solve it locally. Again, keep track of all the Lipschitz constant. Then we can get a long time result. So it is quite technical here also. And then I want to say that to show the weak solutions to good solution is also very technical. Okay. So this is our wellposedness result. So at the end, I have somehow 4 minutes to talk about this convergence result. So here is, again, this convergence is from M-player games goes to the mean field games. And so first we have the Nash system here, okay, with the common noise. Okay, and then so again we somehow derive the weak solution for this Nash system with common noise, because with our little regularity assumptions, we cannot guarantee we have classical solution for this system. So this is system. Okay, and then with so our main contribution here, because this kind of convergence has already started by let me go over some known result is has already started by Cadarlier, Dallery, Lassuet-Lyons in this paper, and also in the book of Camon and Dallery. And then was also started by Dallery, Lacker, Ramana. And this actually they started something more, which is central limit theorem and the concentration of mass, large divisions. And also Lacker himself studied a lot of this convergence result from M-player games to mean field games. And our contribution here is we extend all the result to our weak solution. Okay, so this is the result behind our contribution here. Okay, for the convergence result. Okay, we show so somehow this is the value function for the mean field game, and this is the value function for the M-player games. We show that they converge. Okay. I'll just briefly talk about the result. And then also we show the propagation of chaos. So what I mean propagation of chaos is somehow the optimal strategy for the individual players, so that for the M-player games goes to the trajectory for the mean field games. Okay, there's trajectories. This is for the mean field games, and this is for the M-player games. And I show that this is also converge to 0 as n goes to infinity. And thank you for your attention.